Hello, welcome to another video of CS360, and this video will cover non-determinism and the class NP. So the class NP, I mean, you've probably heard of it, but it actually stands for non-deterministic polynomial time. Okay. And so so to define the class NP, what we'll do is we'll actually define non-deterministic Turing machines. So these are called NTMs. And they're sort of similar to NFAs, and you know how we had like DFAs, and then we defined NFAs. And NFAs were these non-deterministic version of DFAs. So something similar will happen with Turing machines. But with Turing machines, the situation is a bit more confusing. And sort of the reason it's more confusing is that we used to think of Turing machine as computer programs. But then we don't have non-deterministic computer programs. So it's sort of counterintuitive how they might work. Okay, but so, nonetheless, we can define non-deterministic Turing machines. And they kind of work in the usual way that like you have your states and transitions, and like you have things like this, and you have some state that's called the accept state, and you have maybe a state that's called the reject state, and then you also have a tape, right? So you have a long tape, and at each point in time, like there's your head position, there's a position you're looking at. And then, you can write things in the tape. So you can write zeros or ones, let's say, in the tape. So everything works as normal. And the only difference is that this time, given what you're looking at, so given one cell of the tape, right? And given, one state you're at, so suppose you're at this current state. So given a current, input or thing you're looking at, so you're looking at this one on the tape and you're in this particular state, let's say, then there may be more than one transition that you could take. So in a deterministic Turing machine, there's exactly one transition. There's exactly one kind of triple of new state P that you should go to, and then a new character, a 0 or 1 that you should write down. And then like you should either move left or right, so like an arrow, so like, or maybe the character is 0. So you would have this triple that tells you what you should do from this one state and given this one character at the head position. So normally in a deterministic Turing machine, there's one thing to go to, and in a non-deterministic thing, there's a set of things to go to. So you could have another pair here. P prime, or you can go somewhere else, P prime prime 1, you go to the right instead. So you can have a set of transitions that you can take. Okay, so that's the only difference between the definition of a Turing machine and a non-deterministic Turing machine. And okay, so it's still like this 7 double, but the transition function now gives you sets of triples instead of giving you a single triple. Okay, and so, the main question is, how do we define what it means to accept? So for a deterministic Turing machine, we just run the Turing machine, right? We run it. The starting position of the tape, the starting position of the tape is that you're pointed at this blank cell. And then over here, there's some string W that's written, like some string W is written. And then there's more blank cells. And you start right before W, right to the left of W. This is the starting position, and that will be the starting position for a non-deterministic Turing machine as well. And you start at the state Q0, right? So you start there. Okay, but now in a deterministic Turing machine, you just run the Turing machine from there until it reaches its accept or reject states, or forever. If it never terminates, it never terminates. So what about a non-deterministic Turing machine? So a non-deterministic Turing machine is said to accept a string if there is some path you can take that leads to the accept state. So here there's many paths. Some might lead to the accept state, some might lead to the reject, and some might never terminate. There might be some kind of infinitely long path that never terminates. But if there's some finite path that leads to QAC from this starting position, so if there's some way to reach QAC from here, some sequence of writing junk on the tape and moving around in your states that is legal according to these non-deterministic transitions and lead you to the accept state, then it said that this non-deterministic Turing machine that's called N, then we say that N accepts W. If there's just any path that leads it to the accept state in infinitely many transitions. Okay. And note that if there's some path that leads it to the reject state, that tells you nothing. So if some path leads you to the reject state, maybe it rejects, maybe it accepts, you don't know. You need to ask whether there's some path that leads to an accept state. If there's a path that leads to an accept state, the Turing machine accepts. Okay. Now the Turing machine, we said the non-deterministic Turing machine might have some paths that never halt. But we only call we say the Turing machine decides a language if there's no such thing, if all the paths halt within a fixed amount of time. In fact, there must be some number of times such that all the paths halt within that time. Okay, so there are no arbitrarily long paths for one input. Then we say that it actually decides a language. Okay, otherwise it merely would recognize a language. Okay. And kind of more generally, when we're talking about polynomial time computations, then we say that the running time, so the running time, the running time of a non-deterministic Turing machine N on a string W, okay, is the max length of a valid path of N on W. Okay, so if there's paths that are arbitrarily long, if there's paths of any integer length, like they get arbitrarily long, then this is infinity. Okay, so the running time might be infinity of N on W, okay, but we will generally care about the setting where these paths always terminate within some number of steps that depends on W, let's say within, size of W to the 10 steps or something. So every single path, even though there's many non-deterministic paths, all of them need to either accept or reject state within this many steps. Okay, so such a Turing machine is said to run in like N to the 10 time, basically, like in size of W to the 10 time. Okay, but all the paths need to lead to an accept or reject within that amount of time. And similarly, so if all the paths lead to accept or reject state without ever touching more than a certain number of cells, then we can define the kind of maximum space requirement of a non-deterministic Turing machine in an analogous way. Okay, so I won't write that down here, but it's in the notes. So you can define the space complexity of a non-deterministic Turing machine as well. Okay, but remember, a Turing machine, a non-deterministic Turing machine accepting and a non-deterministic Turing machine rejecting are two completely different things. Non-deterministic Turing machine accepting is if some path leads to an accept. And a non-deterministic Turing machine rejecting means all paths lead to reject, every single path. Okay, so like if it rejects within this many steps, then that means, there might be a whole ton of paths. Every single one of them leads to Q reg, like this reject state, and no path leads to Q accept state. But to accept, it just means a single path leads to Q acceptance. So it's very asymmetric. Okay, so returning 0 and returning 1 are not at all the same thing here. It's a very strange situation and a very confusing one. And so if you're trying to program with non-deterministic Turing machines as if they were normal programs, one thing you will encounter is that calling other non-deterministic Turing machines as subroutines is pretty tricky because of this issue of the some path leading to a reject versus no path leading to some path leading to an accept versus all path leading to a reject. So when you call a subroutine, you have to be careful about whether, so if the subroutine might, if you want to, for example, accept when the subroutine rejects, then it's not going to work so well because the subroutine might have a path that leads to an accept and a path that leads to a reject. So you would think the subroutine accepts because of this. But if you now say, okay, if the subroutine accepts, then I will reject. If you try to make a non-deterministic Turing machine that says, if the subroutine accepts, then I will reject, then somehow, now the non-determinism wants to find a path that leads to the accept for the outer program. So for the outer program, you're looking for an accepting path. And that means you're looking for a rejecting path of the inner program. And if there was both an accepting and a rejecting inner path, then the inner program will now kind of reject, even though, if it were to run by itself, then it would be accepting. Okay, but when you run it as a subroutine, maybe it switches to rejecting in order to make your outer program accept. So it's a very tricky. It's very tricky to call subroutines on non-deterministic Turing machines, and I would advise against doing it when possible, because it's so tricky. Okay, one way to think of non-deterministic Turing machines is that there's a guy, he's sometimes called Merlin, is a wizard. Merlin is a wizard, and Merlin knows everything and knows which path you should take at all times. So whenever you encounter a non-deterministic choice, whenever you need to choose whether to take one transition or another, the computation will ask Merlin which choice to take. And Merlin knows everything, so Merlin can lead you to the right path. The problem is Merlin gets paid when you accept. Okay, Merlin gets paid when you accept, not when you give the right answer. Okay, so when you run n on w, suppose you want to check if w is an a, so you want to ask, is w an a? Okay, so there's a right answer, right? Maybe the right answer is no. But Merlin gets paid when you say yes. So Merlin, you're going to run this. Sometimes they're going to be, non-deterministic transitions, so choices of where to go. And Merlin is going to make the choice. And Merlin wants to lead you to say yes. If the answer is no, you better make damn sure that every single path leads to say no. That Merlin has no way of causing you to say yes, if the answer really is no. Okay, but if the answer is yes, then Merlin, then you're good, because then Merlin will try to lead you to a yes. If the answer is yes, you just need to ensure that at least one path of this machine does lead you to output yes, that does lead to accept. Okay, then Merlin would lead you to it. So that's kind of how a non-deterministic machine behaves. And again, it's very confusing, especially when you try to call other non-deterministic Turing machines as subroutines. Yeah, so be very careful about that. Okay. So we can define the class NP then. This is non-deterministic polynomial time. Well, before that, we should define the class n time. So n time of f of n. This is the class of all languages decidable by a non-deterministic Turing machine that takes at most O f of n time, and we already said O f of n time means in every single path is O f of n time. Okay, so so that is the class n time, and then NP is going to be this union of n time n to the k. Okay, so it's the union of n time n to the k. Remember, n time, so this is like n time of n union n time of n squared union n time of n cubed. And remember, these are subsets of each other. So like this thing, we're taking a union to say that NP contains any non-deterministic polynomial time computation for any choice of polynomial that you want, no matter how big, basically. No matter how big k gets, then NP will contain n time n to the k, so long as k does not depend on it. Okay, so this is the class NP. And we can also define nx for non-deterministic exponential time, an NP space, an nx space, and so on. So basically, we can always, for any other class, stick an n in front, and it means now it's on a non-deterministic Turing machine. Okay, and generally that's just going to be a well-defined thing. Okay, so that's the definition of NP. Interestingly, there's an alternative characterization of the class NP. Okay, so the alternative characterization of NP is kind of this verifier. Okay, so the verifier characterization of NP. And this says that A is NP, A is in the class NP. Okay, so A is in the class NP. You know, if and only if A has a polynomial time verifier. Okay, a polynomial time verifier V. And it's really a triple or like a tuple. Like it's a really V, which is a Turing machine. Okay, and also some constants which basically upper bound the polynomial time computation. So when we say polynomial time, we mean that there is some polynomial that bounds the computation complexity of V. So you know, we can put some constants here. How many constants you need? It doesn't matter too much. But okay, so let's put these constants here. These are integers, positive integers. And so what is a polynomial time verifier? So what is this tuple? So we say that V is a polynomial time. So V, if it satisfies the following conditions. So again, this is kind of an if it satisfies the following condition. So basically, for all x in A, okay, we want that there exists a string W, it's called a witness. There should exist a witness W in sigma star. It can be any string, such that the length of W is at most the length of x to the k plus c. So basically, it's polynomial in the length of x, and V of xw accepts. Okay, and then we also want that for all strings not in A, there does not exist W such that this accepts. Okay. So in other words, V of xw has to reject for all W. Okay, and then the final bullet point here is that V runs in time, in polynomial time. Okay, so for example, V of you know, xw runs. We can even bound the runtime only in terms of the size of x, okay, because we know the size of W. We won't care about W's that are too long, and we can check that. So we can even kind of bound this in terms of size of x to the L plus C. Okay, so it is at most. So we can something like this. So V is polynomial time. This is some polynomial. This is okay. What is going on here? V is a polynomial time verifier. It's called. Okay, so V takes in the string x that's supposed to be in A, and takes in a witness, which is basically a string that's supposed to prove that x is in A. Now the witness better be polynomial sized. The witness has to be at most this long. Now, what V is going to do is V can first check that the witness is at most this size. That's an easy thing to check. And then V will perform other checks, okay, to check whether W is a valid proof that X is in A. And this check can be anything you want, okay? So it's any computation that's polynomial time computation and checks whether W is a proof that X is in A. What does it mean for W to be a proof? It means anything you want. You can define what it means for W to be a proof that X is in A. And you just need that there is some polynomial time computation that checks that proof. Okay, for your definition of proof, however you want to define what it means to be a proof. Okay, so if X is an A, there should exist some valid proof that convinces V of this fact. And the valid proof needs to be only polynomial sized in the size of X. However, if X is not an A, there must not be any proof that convinces V that X is an A. So if X is not an A, V can't be fooled into thinking that X is an A, no matter what proof you give it. Okay, so that's a very important criterion here. If X is not an A, it must be the case that V cannot be fooled by any proof. Okay, so you have to check that very carefully. Okay, so if this is satisfied and everything is polynomial, so like the witness size is polynomial, the runtime of V is polynomial in the input, then we say that V, or really this tuple, is a polynomial time verifier for A. This is like a polynomial time verifier for A. Okay, so for a given language, you can always ask, does this language have a polynomial time verifier, or does it not have a polynomial time verifier? It's a valid question for any language. Okay, and so this is what it means to ask that question. So this is the definition of a polynomial time verifier. And our claim is that a language is in NP, it's decidable in non-deterministic polynomial time, if and only if it has a polynomial time verifier. Okay, and it's actually not too hard to see. Why? So first of all, if you have a polynomial time verifier, then we have a non-deterministic Turing machine, right? Suppose we have V. How do we get from V to a non-deterministic Turing machine N, which decides A? Well, what is N of X going to do? What is N of X going to do? N of X is going to basically non-deterministically guess the string W. It's just going to write bit by bit on the tape. It's going to write either 0 or 1 for the first cell of the tape, and then 0, 1 for the next one, 0, 1 for the next one, until it wrote W. Okay, and it can non-deterministically decide when to stop writing W, except it will always stop after this many steps. Okay, so N will non-deterministically write W on the tape just by guessing all possibilities for the first bit, all possibilities for the second bit, and so on. So that takes polynomial time. And then after N wrote W, N can then simulate deterministically, like just it will act as if it's a deterministic machine and simulate V of X comma W. Okay, and then accept if V accepts and reject if V rejects. And now what happens is, if there exists some W that causes V to accept, then there exists a path of N of X that leads to the accept state. Whereas if there does not exist a W that causes V to accept, then there does not exist a path in this computation N of X that leads to an accept state. So therefore, the non-deterministic machine N accepts X if and only if V accepts some proof, some witness W for X. Or in other words, if and only if X is an A. So if we had a polynomial time verifier V, then we would have a non-deterministic polynomial time Turing machine that decides A. Okay, so therefore, if you have this, then you are in NP. So if you have a verifier, then you're in NP. On the other hand, if you're in NP, so if A is an NP, if we have a non-deterministic Turing machine N that decides A in polynomial time, then we can get a verifier. Okay, what would the verifier do? The verifier, the verifier wants X and wants a proof W. What will the proof be? The proof will be kind of the list of non-deterministic choices in the run of N of X. Okay, so the run of N of X only takes polynomially many steps. So there's at most polynomially many non-deterministic transitions it might decide for where to go. And so V is going to consider a proof to be valid if the proof W is the list of all non-deterministic choices of how to make all the non-deterministic choices of this computation in a way that leads to the accept state. Okay, so W will be this long list of, oh, for the first choice, take this transition, and for the next time you have the second time you have a non-deterministic transition, go there, pick this one, and so on. So W is this long list of how to transition when you're running N of X. Okay, so it's this guideline of when you're running this non-deterministic computation N of X and you have to make choices. This is exactly how you should make the choices, and that is supposed to lead you to an accept state. And then what the computation V is going to do is it's going to simulate this Turing machine, this non-deterministic Turing machine n of x. And whenever there's a non-deterministic choice, it's going to read from W where to go. And at the end, V will check that it really reached the accept state. Okay, and now the point of this is that if n really accepts x, that means there's some path that of n of x that leads to an accept state. So there's some string W of polynomial size that causes V to accept. But on the other hand, if n rejects x, then there's no way to get n to go to accept states. So there's no possible string W that will convince V to accept. So V, V will simulate n and it will not reach the accept state no matter what W you give it. Okay, so therefore we converted a non-deterministic Turing machine n that decides A into a polynomial time verifier V. Okay. So it's not too complicated, but it's kind of a neat conversion. The nice thing is that the polynomial time verifier V is a deterministic Turing machine. So V is deterministic. Okay, so it's V is a Turing machine, not an NTM, it's a TM. So that's pretty nice because we're familiar with Turing machines, they're like programs. So if ever you're confused about non-deterministic Turing machines, which are this non-familiar thing, there was a Merlin there that I said might help with intuition. You don't need any Merlin for V. V, the verifier, is a deterministic program. Okay, and sort of intuitively, NP is you can think of NP as a class of puzzles where you can check the solution to a puzzle in polynomial time. Okay, so a language A, okay, is an NP. If A is an NP, what does it mean? If A is an NP, then it means that, well, it means there's a polynomial time verifier for A. Okay, which means that when X is an A, then there exists a witness for X. There exists some witness for X. Maybe I should call it W subscript X. There's some witness for X, which proves that X is an A. Okay, so the question of deciding whether X is an A is the same as the question of deciding whether a witness exists. So we can think of this as sort of a puzzle where X is an instance of a puzzle, or maybe an instance of a solvable puzzle. And the question of whether X is an A is like asking, is the puzzle solvable? Does the puzzle have a solution? And then W here, or WX, is a solution to the puzzle X. So for example, you can think of A, here's an example. A is the language of all Sudoku puzzles, like generalized Sudoku, like n by n Sudoku puzzles. So these are partially filled n by n boards for which a valid Sudoku solution exists. So A is this solvable Sudoku boards. Like if I, you can imagine if I give you a Sudoku, whatever, I can't, probably pretty bad at drawing Sudoku, but if I give you a Sudoku board like this, and I put some numbers in. Okay, so some ways of putting in numbers will not be solvable. For some ways of putting in the numbers here, there won't be any valid solution to fill the rest of the cells to get a valid Sudoku board, like a filled Sudoku board. So A contains the class of all Sudoku puzzles that have a valid solution. Okay, now classically Sudoku puzzles have a unique solution, but here we're not going to require the Sudoku puzzle to have a unique solution, just to have some solution. Okay, and A is all n by, so it's generalized Sudoku, it's like on n by n boards. And then A will only contain the partially filled n-band boards for which a solution still exists. So now we claim that A is an NP. Why is it A in NP? Because given such a board, I might not be able to solve it efficiently. To know whether there is a solution seems difficult. But here's what I can do. I can verify a solution efficiently. If somebody gave me a solved version of this puzzle, so if somebody gave me both this puzzle and an actual solved version where like every single thing was filled in, like all the numbers were filled into the cell here. All I would check is, first of all, I would check that this is a valid Sudoku board, and I will also check that the numbers that appear here really are there, like it wasn't cheating by erasing something. So I could easily check in polynomial time that this is a valid solution. And so the verifier will basically do exactly that. The verifier will take like X and W, X, and just check that this is a valid solution for the puzzle X. Okay, so this is in this sense, NP can be thought of as a class of puzzle languages for which a solution to the puzzle can be verified in polynomial time. So you may not be able to solve the puzzle in polynomial time necessarily. Maybe sometimes you can, sometimes you cannot. That depends. But you can verify a solution to the puzzle if somebody gave it to you. And note that this is, again, asymmetric. If there is a solution to the puzzle, it's easy to verify. If there's no solution, maybe the fact that there's no solution is hard to verify, right? So if somebody gave me somebody told me this board is not solvable. Okay, that seems hard to prove. Like how would I prove that a Sudoku board does not have a valid solution? I mean, you could check all the possibilities, but that's like an exponentially long check. Like, right, if there's n empty cells, then I would have to do like 10 to the n or whatever ways of filling all the cells. Like it's exponentially many ways to check that there's no solution. Maybe there's an efficient algorithm, but it's not obvious that there is one, right? So to be an NP just means that you can verify a valid solution to the puzzle if there is one. But if there's no solution, maybe nobody's forcing you to be able to prove that. Okay, you only have to be able to prove that when there is a solution. So if X really is an A, there needs to be a proof of this. If X is not an A, there does not need to be a proof that X is not an A. The only condition is that you can't falsely prove X is an A, right? Like the only condition we have here is that if X is not an A, then V better reject. V of XW must reject. So that just means if X is not an A, then any proof that X is an A will not be a proof, will be wrong. And V will catch the flaw. But that doesn't mean that V can prove that X is not an A, right? It doesn't mean that V here can't necessarily prove X is not an A. It can't verify that. V only fails to verify that X is an A, right? So V rejects any proof that claims to prove that X is an A. Okay. Okay, so maybe one last thing to say about NP. So one thing that appears about NP is in the last lecture of the notes, we prove that if P equals NP, then it would actually mean that we can find the witness efficiently. Okay, so essentially, okay, so first of all, P versus NP is a a long-standing open problem. Most people believe that P does not equal NP. Okay, because just because you can state a puzzle, and NP contains sort of fully general puzzle, anything you can verify quickly. But just because you can verify something quickly, it doesn't seem to imply that you should be able to solve it quickly, right? Like just because you can check a solution quickly, that means you're in NP. It doesn't. It would be counterintuitive if that automatically meant you can find a solution quickly or solve it quickly. Okay, but in the last lecture of the notes, what we show is that if P equals NP, so if this counterintuitive thing happens, then given X, given x in A, where A is an NP, with verifier V. So given a string x in A, where is a language that has verifier V, we can find the witness W such that V of xW accepts. And we can do this in polynomial time. Okay, so if p equals NP, then given x in then given an input, we can actually find the witness. Not only can we decide whether the string x is in A, of course we can decide that because if p equals NP, then A would be in P. But we can even find the witness that proves that x is in A, if indeed x is in A. So in other words, not only can we decide whether a given Sudoku puzzle is solvable, we can even find the valid solution. Okay, and so if p equals NP, then we would be able to solve arbitrary puzzles. Not only to tell you whether the puzzle is solvable, but actually to find a valid solution to the puzzle if one exists. Okay, and the way to show this is to sort of you can kind of well, this appears in the notes. I'll only sketch the proof here. But the sketch of it is that you're looking for this witness W, and you can try to find one bit of W at a time, right? So you can try to first ask, is there a valid witness for X? Like, does there exist a valid witness for X whose the first bit of W is 0? Does that exist? Okay, and if the answer is no, then is there a valid witness for X whose first bit is 1 instead? Okay, and maybe the answer is yes. And the idea is that any such question is a decision question, which itself has a verifier. It's a decision question that itself is in NP. Okay, it's a decision problem, and it's easy to verify the solution to that decision problem if the answer is yes, because you can just give the witness W. So and this appears in notes formally, but the informal argument is that I'm going to give a bunch of decision problems here, all of which are in NP. And if p equals NP, then therefore all these decision problems must also be in P, and they each have a polynomial time algorithm, right? So essentially, the idea is I'm given X, I'm trying to find W, and what I'll do is I'll first ask the decision question, does there exist a witness W for X whose first bit is 0, right? And that's a decision question, and you can show that it's an NP. And therefore, you can decide this in polynomial time, assuming p equals NP. And then this way I can find the first bit of W. And after I found the first bit, I can then find the second bit. I can say, okay, so the first bit was 1. So is there a witness for X whose first 2 bits are 1, 0? And if the answer is yes, then I'll ask, is there a witness for X whose first 3 bits are 1, 0, 0? And maybe the answer is no, and okay, I'll go with 1, 0, 1. And this way, I can basically find the bits of W by breaking it up into like length of W many decision problems. And each decision problem for finding that bit of W will essentially be a problem in NP. So you have to work a bit to show that it's in NP. And because it's in NP, then assuming p equals NP, then it's also in P. And so I can, in polynomial time, decide all of these questions and therefore find the string W. And there's only polynomially many such questions because there's only polynomially many bits to the string W. Okay, so that means that given input X, I can actually find the witness W that proves that X is in A. So in other words, such that XW, V of XW accepts. Witness finding, would be in polynomial time as well, would be possible in polynomial time if P were equal to NP. Okay, and that kind of means that sort of given an arbitrary computation, given the description of suppose that somebody gave me the description of a machine V, and also they gave me a string X, and they gave me this pair, and V was polynomial time, and they basically asked, they had basically asked me, does there exist a string W that causes this machine that I gave you to accept the pair X comma W? Does there exist a polynomial sized string W such that this accepts? So if somebody asked me this question, then this question would in fact be in NP. Okay, this question would be in NP. If P equals NP, then I would have some polynomial time algorithm for automatically solving this. So this is a polynomial time algorithm for automatically deciding whether there is some string that V will accept, or V of X comma something, some string W here to put in this dot, some string W to put in this dot that causes V to accept. It would seem intuitively like the only way to know whether V will accept a string would be to run V on that string. Okay, but here we have exponentially many strings to run on. So it would seem intuitively that we cannot tell whether V will accept some string without doing exponentially many steps of computation. You know, at least one, but you know, probably many steps for each string W. So for each string W, we would have to do many steps of computation. So that seems very intuitive that you know, because there's exponentially many possibilities for the string W, then we cannot decide whether there's such a string W that causes V to accept in only polynomial time. We would need exponential time. Okay, but proving that would require proving that P not equal NP. Okay, so we believe P does not equal NP, but proving it well appears to be extremely difficult. We would like for there to be some kind of theorem like the time hierarchy theorem that tells us that we cannot do this, that P does not equal NP. But you know, there doesn't seem to be such an argument, and in fact, we can even formally show that there is no argument that works by diagonalization. There is no argument that works like the time hierarchy theorem, but shows you that P does not equal NP. So that's not covered in this course, but that turns out to be a barrier. It's called the relativization barrier sometimes for showing that P does not equal to NP. Okay, that's all for this time.